x of m, right? X of n minus m, when m is a positive number, is shifting the whole function left or right? How many say shift? How many say? Let's say x of n is like that, right? Say m is 1, for example. So x of n minus 1, is it shifted to the right or shifted to the left? Left or right? Right or left? See, if you have a function x of n, right? X of n, and this is the function. Say this is the function, right? This is 0. This is n, right? Okay. And when you have x of n minus 1, is it this case, or is it this case? Which case is it? Is it this one or this one? How many say is the first one? How many say is the second one? How many don't know? It's the first one. For this kind of things, right, it can be very, we learn convolution, your brain can be very convoluted. Right? It's always easier to just plug in some number to test. Okay? For this case, right, to achieve x of 0 here, right, your n must be at n minus 1, right? Then you achieve the x of 0 earlier, right? So when you see a function x of n, when you see a function x of n minus 1, it means the function shifts to the right, understand? Okay? So coming back to here, if you have a function x of n, and your Fourier transform is capital X, right? Now, if you shift the function to the right by m steps, right? Assuming m is positive number, right? You shift the function to the right by m steps. The derivation that we went through last time shows you that the result of this shift, right, in the time domain, what it manifests, the shift will be manifested in the frequency domain. And how it manifests itself is by multiplying by a e to a minus j term, the phase term, understand? Why do I say e to a minus j something is a phase term? What is the magnitude of, okay, this is another question I want to ask you. What is the magnitude of e to the power j theta? What is the magnitude? Equal to what? Equal to what? Remember, j theta is cosine theta plus j sine theta, right? The magnitude of cosine theta plus j sine theta is equal to square of real part plus square of imaginary part, right? Yeah? And what is cosine square plus sine square? 1. Okay? When you are playing with this kind of e to the power j something, and if you are asked to do the magnitude of e to the power j something, you should be very happy because it's just 1, understand? Okay? Okay? So it is just a rotating vector of magnitude 1. Okay? A rotating vector of magnitude 1. Okay? Rotating vector. So it's a phase, right? So when e to the power j something multiplied with any number, which is any complex number, right? Is it going to change the magnitude of this complex number? Yes or no? No, right? It's not going to change the magnitude. j theta to a. Right? What is going to change here? It's going to say, how do you do the multiplication of complex numbers? You multiply the magnitude together, right? And then the phase angle is the phase angle here plus the phase angle here, right? Yeah? You did complex numbers, right? I assume you all do complex numbers before. No? When you multiply two complex numbers, just remember this if you haven't done before. When you multiply two complex numbers, the product, the magnitude of the product is the product of the two magnitudes, okay? The two magnitudes here, right? And then the phase is the phase angle here plus the phase angle here. If you don't understand this, I think I cannot spend time teaching you complex number here. You should have done it in your prerequisites, right? If not, then if you remember, if you forget it, you have forgotten it, go and read out on your own, okay? Okay? If you don't know how to do complex numbers, you cannot understand, you cannot go on. Okay? So, since the magnitude here is equal to 1, so the magnitude of the A is not going to, so the magnitude, so when you have e to the power of minus j theta multiplied by A, which is A is a complex number, is equal to the magnitude of A plus the phase angle of A plus minus theta, understand? Minus theta. The two phase angles add together, right? The phase angle of A minus theta, okay? This is the phase angle, the phase. Alright? So, no. There are mathematical skills here that you need in this course, but if you don't understand, you have to let me know, understand? I'll get the TA to coach you. It happened before. Somebody don't even understand what is a vector multiplication. I don't know why they can come to this course without knowing it, because it's prerequisite. So I get the TA to coach him. Right? So if you're supposed to know complex numbers, you come here, don't know complex numbers, let me know, right? It's not the end of the world yet. Let me know. I'll get the TA to coach you, alright? One-to-one coaching. Alright? So don't be shy if you don't understand, alright? If you don't know, you have to tell me, Otherwise, I can assure you, you'll be lost. You'll be lost, I can assure you. So take it seriously, right? Now, so the Fourier transform of a signal that is shifted to the right by m steps is equal to the same Fourier transform without shifting multiplied by a phase term. And that phase, the m steps here, the m shows up in this phase here, understand? Minus j2 pi k m over n. Okay, that's for the discretized case. For continuous case, it's the same thing. So I'm going to I'm going to use the same result here. I'm going to use the same result here. Right? Okay? So we were here just now, right? We take out the x of tau. And then you have this multiplied by here. Right? So inside here we recognize just now that is another Fourier transform, but this time the Fourier transform is a shifted version of t, right? Of h, right? Shifted version of h, right? And we know that shifted version of h, no sweat, is just h of f, the unshifted version, multiplied by e to the minus j2 pi f tau. Tau is the shift here, understand? Yes? Okay? That's what we saw just now, right? We're just using it in the continuous time domain. Now you have something very interesting. Now this is integration with respect to tau, right? And h of half here has got nothing to do with tau, right? It's a constant here. So you take out the constant. right? And you're left with x of tau e to the minus j 2 pi f tau d tau. What is this? This is just another Fourier transform, isn't it? Yeah? So it becomes h of f multiplied by x of f. So how nice. In other words, the Fourier transform of the convolution result, which is a capital G, is simply h times x of f. Point by point multiplication, understand? So instead of doing multiply and sum in the time domain, and you use a lot of for loops for that, and it takes a lot of time, right? What you need to do is transform this into frequency domain. Transform this into frequency domain. Just point by point multiplication. Okay? And to get back the time domain G signal, just inverse Fourier transform, right? Right? Okay? Okay? And this is continuous time Fourier transform of convolution. This is linear convolution. Remember, this is called linear convolution. We are doing linear convolution in the time our intuition is on linear convolution on the bell and the gong, right? Now, when we do Fourier transform, right, I think almost 100% of the time we use FFT, right? FFT is a top form. You remember. Fast Fourier transform is what kind of Fourier transform? Is it the continuous time Fourier transform? Yes or no? Is it a discrete time Fourier transform? Yes. Is it a discrete time Fourier transform? How many say yes? How many say no? How many say yes? How many say no? All wrong, understand? Discrete time Fourier transform. Remember discrete time Fourier transform, the frequency axis is still continuous, understand? There is another one, the final one, the ultimate one is discrete Fourier transform. Everything else is discretized, understand? So FFT is a fast implementation of DFT, the discrete Fourier transform, understand? Okay? There's a difference between discrete Fourier transform and discrete time Fourier transform, alright? Okay? And most of the time we use FFT, which is a discrete Fourier transform, right? Now, when you do discrete Fourier transform, what kind of strange things comes into your mind? What kind of strange things come into your mind? What kind of strange things come into your mind? What kind of strange things come into your mind? What do you think? Periodic, understand? Everything is periodic. And so when everything is periodic, it does not, all our intuition cannot work anymore, right? Because the bell, when you hit it, ding, it doesn't ding, ding, it doesn't work this way, right? But the moment you use discrete Fourier transform, which is FFT, you have to know that the mathematics assume it that way, right? Right? So what should you do? I just hope one day I can take off my mask. This is the 5th week already, right? This cough, I don't know how long it's going to last. Now, in order, but we still want to use FFT to implement our linear convolution, right? Right? Because it's so efficient, right? So one way, which you'll see later, I'm giving you some preview. One way of doing this is this, you should cheat the system, understand? Right? Because you say the bell doesn't go this way. Ding, 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 the bell doesn't go this way, right? Right? But when you do FFT of ding, right, it's going to assume this way, right? So what you need to do is this. Listen, you have to manually go and add some zeros to it, understand? Instead of ding, you say the Fourier transform, the impulse response of the bell is ding, 0, 0, 0, 0, 0, 0, 0, right? Right? And you do that for the other signal. And once you do that, right? Once you do that, you find that actually it doesn't matter if it assumes periodic, right? Because it's too far away to affect your result, understand? Okay? So the way to use FFT to implement your convolution is to add zeros to your signal. How many zeros to add? You find out, I'll show it here and you do it in your next tutorial. By the way, the next tutorial I'm going to give out tonight, the next tutorial is a very important tutorial. Make sure you do it very, very well because you're going to need it for your project. Okay, you're going to need it for your project. Huh? So, and I think I find it fun to do it. I find it fun to do it. I hope you find it fun to do it also. Okay. So convolution can be done very efficiently using fast Fourier transform, which is the form of discrete Fourier transform (DFT). Yeah? Now, when we use FFT, however, the signals in both time and frequency domains are periodic, right? Right. So when we use FFT to implement convolution, we end up performing something called circular convolution, right? I'll illustrate what circular convolution means later, right? Because the signal repeats itself, right? So instead of, so when you slide, when you have two signals, right? You multiply and sum, right? Right. When you slide out, you're not seeing zero, no, you're seeing this guy here, understand? Because it repeats. The signal, you do multiply and sum, right? Right? When you're here, you multiply with zero, right? In the linear convolution case. But when you use FFT to implement, it's not zero, no, because this thing repeats itself, right? Right? So you're going to hit this guy again, no? Right? So this is something called circular convolution because the array is like circularly shifted. Understand? So this is called circular convolution. So this, the following slide, right? The next slide is a repeat of what we saw just now, but in the discrete time domain. Discrete time domain, huh? So x of n convolved with h of n is x of tau, h of n minus tau, and tau sums from 0 to n minus 1. Right? Now we are talking about periodic case already, right? The period is m, capital M. Okay? So you do the same kind of mathematics, same kind of derivation, you end up with this formulation, which is exactly the same as the continuous time case, right? So this is just to show you that in the discrete Fourier transform case, the theorem is still intact. Understand? So to perform convolution in the frequency domain, what you need to do is you convert all of them into frequency domain, right? Perform convolution in the time domain, you do it in the instead you should do it in the frequency domain, right? So h of n becomes h of k, x of n becomes x of k. Instead of the very cumbersome operation of convolutions, shifted sum, you just need to multiply here, right? Pointwise multiplication on respect to k, and then you get the result. And then you just do an inverse FFT, you get this, understand? Okay? So in circular convolution, the values in an array get circularly shifted, right? So when your input is 38215476, right? When you do the shifting, right? This thing doesn't shift outside. And then you don't have a zero that shift in. In the linear convolution case, on the left hand side, you get zeros that shift in, right? You shift this way, right? Right? Instead, the circular convolution, this guy will come here. You shift this way. So it's circular shift. Okay? Now, circular convolution implemented in time domain, when you have input of all ones, right? And you have output of all ones, right? When you do circular convolution, you get the output of all ones also. Remember in the linear convolution case, when you have two rectangular functions, right? When you do the linear convolution, what kind of shape do you get? You get slanted, right? 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 But circular convolution not like that, because when you shift out, you still see the next period. Understand? No matter where you shift, it's all see all one, right? So, and then using FFT, confirm that it is the case, right? So this is to show you that if you do the FFT way of convolution, you are doing the circular convolution. Alright? So this is another view of circular convolution. Now this is assuming you have the signal x, which is like 1, 1, 1, 1, 1, 0, 0, 0, 1, 0. This is x, huh? Right? No. You take this as one period, right? Right? Now I'm going to, for display purposes, I'm shrinking the time axis. Instead of 9 seconds, I have 20 seconds here, right? Right? So this 9 seconds here is represented here, understand? 1, 1, 1, 1, 1, 0, 0, 0, 1, 0. 1, 1, 1, 1, 1, 0, 0, 0, 1, 0, understand? Yeah? So this is one period of the signal, right? One period of x. But we know that we're going to use FFT to implement the convolution. So we have to be aware that this thing repeats outside here and repeats outside here. Okay? There are something here, not zero anymore. Okay? Now, the second signal, the H, right? The H, right? H is 1, 1, 1, 0, 0, 0, 0, 0, 0, 0. So H is 1, 1, 1, sorry, one period of H. Okay, sorry, this 1, 1, 1 followed by 7 zeros, right, is for H, right? And then I'm representing it here, right? 3 ones and then followed by 2, 4, 6, 7, 0, right? So this is one period of H, right? This is one period of X and this is one period of H. Okay? To do the convolution, what do? You must flip the H first, right? Right? So you flip the H with respect to the 0 axis and then this part here becomes this way, right? Yeah? Yeah? But be careful because earlier on, this outside here are not 0, right? So when you flip this thing here, will come in here or no? Understand? Okay? Okay? So then when you do the convolution, right? When you do the convolution, it's not just this and this, right? It's not just this and this multiply because you have these and these also multiply with the values here. Understand? So that's not what you want, right? That's not what you want. But this is what happens if you use FFT to do convolution. Okay? So, right? So what happened is this, listen very carefully. If you don't want these guys here, because these guys when they flip, you come here and then you go and multiply with your values here, right? Right? Your H here, when you flip, you multiply with the X here, right? It's no good, right? Right? So in order to ensure that these people don't come and disturb your convolution here, what you need to do is to add a lot of zeros to your left and right, right? And because it's periodic, you just add to one side, it's fine. Okay? Get a lot of zeros so that when you flip, you see all the zeros. Okay? Okay, so this is circular convolution, right? And the first step is this, right? The first step, you see, the first step is this. You flip the H, right? You flip the H, you flip. This is one period of H, right? Then you flip, you get this, right? Okay, but this thing here get flipped here. But fortunately, your X, it get flipped here, right? So this flipped version of H, you multiply with X here, right? Alright? And then you disturb your convolution result. It's no longer linear convolution anymore, right? Right? Then the next step, so just now here, this multiplied by this plus this multiplied by this, you get the result here 2. Okay? And then you have to shift this to the right, by one step. This multiplied by this plus, this multiplied by this plus this multiplied by this plus this multiplied by 0 here, we'll get another 2, right? Right? And then you shift to the right. This multiplied by this plus this multiplied by this plus this multiplied by this and then plus all the zeros here, you should get the 3, right? The 3 here, right? And then you shift so on and so forth. Okay, then you get this result. Okay, so this is circular convolution. Now, so MATLAB has got, later on I'll demo to you how to use MATLAB to do all this. MATLAB has got built-in functions for you to do convolution. You can use it, but actually I don't, for demo purposes I'll do it, but I don't, for understanding, for the purpose of understanding, it's better to go and code your multiply and shift, understand? Then you understand better. Sometimes using library is a terrible thing. How many of you had attended the computer vision and pattern recognition course, CS2108? Let's see. Were you all using OpenCV? Yes. Okay. I was teaching that course last time. And I let the student use OpenCV, which is a very big library. After that, banned them from using it. You know why? Everyone uses the OpenCV library, gives me very nice results and things like that. But I ask them, how does this work? Why it doesn't work? All don't know, because it's all library. Don't learn that way. Okay, code yourself. Then this is not a race to get good research result. This is understanding fundamentals. All right. When understanding fundamentals, don't go and use high level libraries. Okay. So that's for convolution, right? I'm going to demo to you. I'm going to demo to you some okay, let me open another script. Okay, you can see my make the font bigger. Is there a font here? View. The words are too small, right? Huge one. Yes. Okay. 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 Now, if I have an array A equal to 1, 2, 3, 4, 5, okay? And then if I have another array called, okay, this is my x, I use x here, and this is my h, right? H is like, I call it 1, 1, 1, okay? 1, 1, 1, or maybe 1, 2, 1. Okay? Right? Now, to do linear convolution of x with h, right? You have to use x here, and then you have to flip the h and multiply and sum, right? Right? Now, you can write the for loop to do it, right? But MATLAB actually has got a function. See, convolution. And MATLAB COMP is a linear convolution. Okay? It's a linear convolution. So I'm going to do, right, C equal to x, convolve x with h, right? And then I'll say demo 1. Okay? Then demo 1. Okay? So you have x, you have then your C is this. See, your X is 1, 2, 3, 4, 5, right? X is 1, 1, 2, 1, right? So when X is shifted, is flipped, you have 1, 2, 1 on this side, right? Right? And all 0, right? So when you multiply and sum, what do you get? You have 1 times 1, right? Yeah? So the first answer is 1. Right? And then after that, your 1, 2, maybe 1, 2, 1 is a better example. Let me use 1, 2, 1. I use 2, 3, 1, for example. Okay, then I run again. Right? X and H and C. Okay, so X is this and H is 2, 3, 1. When you flip H, it becomes, you flip this side, becomes 1, 3, 2, right? Yeah? So 1, 3, 2, you multiply the 1 and 1, you 1, 3, 2. You multiply 2 and 1, you get 2, right? Yeah? Right? And then after that, the 1, 3, 2, you move here. So 1, 3, 2. 3 times 1 plus 2 times 2 is 7, right? Right? And then you move here is 1, 3, 2. 1 times 1 plus 3 times 2 plus 2 times 3 is 13. Alright? And then you slide further, so on and so forth. Understand? And notice something here. What's the length of H? X. What's the length of X? 5 items, right? What's the length of H? 3 items, right? What's the result of the convolution? 7 items, right? So it's 5 plus 3 minus 1, understand? Result of the convolution, because of the shifting like that, it is the length of the signals add up together minus 1. And this becomes an important number, right? You tell you how many zeros to add later, right? So the result of the linear convolution is length of X plus length of H minus 1. Okay? So this is linear convolution, right? Now, you can also do circular convolution using MATLAB. Huh? If you do circular convolution, right? Let's say circular convolution, CC, is equal to circular convolving X and H. Okay? And for circular convolution, we have to tell them what's the length of the signal you want to convolve. Understand? So I have length of X. Okay? 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 So H will be automatically padded with 2 zeros, right? To make it 5. Understand? Now I'm specifying my circular convolution is a length of 5. Understand? So H doesn't have 5, right? 3 numbers only, right? You automatically type with 2 zeros. Okay? And then you print out your CC, your circular convolution. Right? So now you see that your C and your CC are different now, right? Right? Because in circular convolution, everything everything is periodic and things like that. Okay? Okay? Now listen. How do you so this is not what you want, right? Circular convolution. Now the trick to use circular convolution to get the same linear convolution result is to add everything zero to zero, understand? Because if everything is zero, right? If this is a signal of interest, this is a signal of interest, you add all zeros to it, right? Right? When you flip and then everything periodic, right? Periodic, but you happen the periods, your real signal start very far away, right? Right? So it won't affect the periodicity doesn't come in that sense. So let's say DD is equal to circular convolution X and H and length of and the convolution. Now I want to use X of length of X plus H minus 1. Understand? now I say I want a circular convolution of 7 points. Okay? That means x will be given by the original 5 numbers plus 2 zeros, understand? Then h will be given by the original 3 numbers plus 4 zeros. Okay? Once you do that, you can see that actually the circular convolution result will be the same as the linear convolution result. See? Your circular convolution and this is your circular convolution result, this is your linear convolution result. They are exactly the same now, right? Yeah? Yeah? Okay? So what do we learn here? What we learn here is we know the importance. Okay, rewind to last lecture. We know the importance of doing convolution, right? Because convolution allows you to know what you hear if I hit the bell in certain way, right? You just need to know if I hit the bell, what do I hear? The impulse response. Now I know everything about the bell. You tell me how hard you hit and what's the interval you hit. You tell me the hitting pattern, I can tell you what you'll be hearing, right? So that's how powerful convolution is, right? But we also know today that if you do the convolution the intuitive way, it's going to take a long time, right? Right? But then if you do it in the Fourier transform way, it's extremely simple. Okay? Okay? But the Fourier transform way, you have to deal with the periodicity. And the way to get around the problem is add zeros to your signals. So that the periodicity you have to pop out away wouldn't affect your result. Understand? Okay? So let's see. If I do it the Fourier transform way, right? So you have the x, right? So let's say capital X is the Fourier transform of x, right? Capital H is the Fourier transform of h, right? Okay? Now, if your G, capital G is the Fourier transform of x multiplied by h. By now you should know what is the meaning of dot star, right? Dot star is two arrays multiplied together without any summing, understand? Right? When you do a star alone, it's a matrix multiplication. Huh? When you do this, it's point by point multiplication. Right? And then you say G is equal to FFT of G, right? Inverse FFT of G. Right? So let's see what is G. Right? Let's see what is G. No, sorry. You can't do this because X and H are of different lengths, right? Right? So I have to say, I use the length of H, for example. The length of H, which is 5, right? And FFT, the length of H, which is 5. And then this is not going to give us the result that we want, but see what is it? Oh, what's that? Sorry? Oh, sure, no one back again. Okay. So you have X here, right? You have H here, and then you have the G, which is 13, 10, 13. No. I shouldn't use X of H. H is shorter than X, right? I should use X of length of X, right? And this will not give us the result we want either, because circular convolution, right? It's 21, 12, 13, 19, 25, right? It's the same as this one, right? Circular convolution, can see that, right? So when you use FFT way, you get the circular convolution result. Okay? Okay? Now how to get the linear convolution result? Instead of just using, so you have to add zeros to it, right? Your FFT, see, when you have an array, right, of let's say 10 numbers, when you say FFT, you say I want a 12-point FFT, right? You say 12 is behind. The FFT function will add zeros to it, understand? They'll pair, so-called padding with zero. That's what people say, padding with zero, okay? So you want, what's the length of x and h that you need, the minimum length that you need, so that you get your linear convolution result. Length of x plus length of h minus 1, right? Right? But if I don't want, I kiasu. For those of you who are not Singaporean, you probably don't know what is kiasu. Kiasu meaning, kiasu is a local Hokkien word that means scared to lose, understand? You are afraid to lose, so kiasu. You kiasu, you add many zeros, it will still work, understand? So kiasu, you add many zeros. How come it can't? I short of. Where does it hang? Where does it hang? Okay. So your G will be this, right? Remember, you see now your result comes, your linear convolution result is here, right? Your linear convolution is what C, right? 2, 7, 13, 19, 25, 19, 5. 2, 7, 19, right? And the rest are all zeros, right? So if you kiasu, you add many zeros, you still work, understand? Understand? You kiasu, many zeros, you still work. Now, you cannot be always kiasu, right? Right? You want to know what is the minimum you need to add, right? And the minimum you need to add is what we showed just now. Length of x plus length of h minus 1. That's the minimum length you can use to avoid the circular convolution effect, understand? Okay? So let's do the minimum way. The minimum way, which is minus 1 here. Right? And then you get the answer you want, right? And this is the same as the linear convolution result. Okay? Okay? So in other words, we know that again we know the importance of doing convolution. You just need to know what the impulse response of your bell, right? I know everything about the system because now you tell me what's the hitting pattern of a bell. It doesn't matter. You tell me your pattern, I can tell you what you'll be hearing, right? Now, in order to do that, then we need to do multiply and sum, shift, multiply and sum, which is very cumbersome, right? In the time domain, you do it in the frequency domain. It's just in fact, you can do it in just one statement, right? And then you can get the result. But you have to take note that you are dealing with periodicity. So the length of the signal you better paired with zero. Understand? You pair with zero, then you get the result that you want. In fact, you can actually see G can be written as inverse FFT of x, length of x plus length of h minus 1, and FFT of h, length of x plus length of h minus 1, right? And then multiply. And right? You can actually do the convolution process, get the convolution with just one statement, okay? Instead of a lot of for loops, okay? And not just avoiding for loops, because FFT is a fast implementation of DFT, right? So you have a lot of speed improvement there. And now you tell me if I hit the bell in this way, what would I be hearing? All you need to do is you tell me your hitting pattern and the impulse response of the bell. I plug it in. Impulse response of the bell is h. Your hitting pattern is x, right? I plug into one statement like that. I'll be able to tell you what you'll be hearing. Understand? Okay? And the computation is extremely fast. Any question? If not, we go for 5 minutes break. It's 11:01. we resume at 11:06. I will email you this set of codes, right? You can play with it. Right, let's continue. Now, you see, we do so much of Fourier transform for various reasons. One of the reasons is to know what are the frequency content in the signal, right? The frequency content in the signal. And knowing the frequency content in the signal is important because there are certain things that you just have to analyze in the frequency domain. It doesn't matter how large I speak. It doesn't matter how large I speak. Understand? Do, re, mi, fa, sol. Do, re, mi, fa, sol. Both are the same, right? It's just a tuning up the volume of your radio only, right? Right? So, in other words, when I say this is the time domain, this is the time domain, right? Right? Do, re, mi, fa, sol, I get this, right? Yeah? This is the volume, right? This is the volume, which is the amplitude of the air vibration, right? Air vibrate very, very big amplitude is louder voice, right? And this is do, re, mi, fa, sol, right? Right, I'm a poor drawer, but assuming the two shapes are the same. It's just that the volume is a lot lower, right? Right? Do, re, mi, fa, sol, do, re, mi, fa, sol, they are the same, right? So in other words, when you want to analyze music, it doesn't help to analyze it in the time domain, right? Right? Time domain doesn't give you anything. You have to learn to see in the frequency domain. And in the frequency domain, the do, re, mi, fa, sol is this, right? The frequency domain is here. Frequency domain is here. Do, re, mi, fa, sol is like that. Do, re, mi, fa, sol, right? And the rest are all zero, right? Some frequencies, do, re, mi, fa, sol, right? And then here, same thing. Do, re, mi, fa, sol, right? Right? Okay? And if they are same magnitude, same do, re, mi, fa, sol, all, assuming all the 5 Qs are the same amplitude, you get the same height here, right? And same thing here, you get the same height here also, understand? Understand? So all that, but in this domain, that is better now because you know that other frequencies are not present. Only certain frequencies are present. And the 5 frequencies all happen at the same magnitude. Right? And the 5 frequencies also happen at the same magnitude. And you say that they are the same signal, understand? Because loudness does not matter, understand? Loudness does not matter, understand? Okay, for example, if you have another signal in the frequency domain, right? If the signal is like that, and then you have another one, the signal is like that, right? They are the same shape, for example. They are the same shape, it's just a different thing. You say they are the same, understand? Okay, in the frequency domain, you don't care about the magnitude anymore because what they care is the relative frequency, right? You have what's the frequency of do compared to re, for example, because the difference in the frequency will give you different sound, understand? Okay, so one of the reasons we want to see things in the frequency domain is because, for example, you want to analyze speech or you analyze music, you cannot see it in the time domain. Time domain does not tell you anything. Time domain tells you the loudness, which is of no interest to you, right? So you see in the frequency domain. That's one reason for using Fourier transform. The other reason for using Fourier transform is, as we have seen just now, if you want to check, the impulse response and what will I be hearing after hitting the bell, right? What will I be hearing? If you do it in the frequency domain, it's a lot easier, right? Just one statement in MATLAB, just one statement, you can get the result. No need a lot of for loop, and it's a lot faster, right? So, and there are many other reasons for using Fourier transform, right? Now, the next topic that we want to cover, the next topic that we are going to cover is something called sampling. Something called sampling. I'm going to give you some overview first. I give you overview, and then next week then we go through the slides. Okay? Overview here. And it's a lot of intuition behind. A lot of intuition, A lot of intuition. Now, if I have a signal in time domain that varies very slowly, right? And I say I want to change this signal into keep this signal in an array, in a computer array, right? So when you want to keep things in an array, you have to discretize the time axis, right? Then you say what's the amplitude here, what's the amplitude, so and so forth, right? So you need to discretize the time array, the time axis. And when you discretize the time axis, this process is called sampling, understand? This is called sampling because it samples the signal at discrete time intervals. It samples the signal at discrete time intervals, right? Now, if the signal varies very slowly, right? It's a low frequency signal. So it's like that, right? Very slowly, right? Do you think you can afford to be lazy and sample now? Wait for a while, sample again, after that just interpolate that. Can you do that? Can you afford to do that? You can, right? Because the signal doesn't change so fast, right? So your sampling frequency, how fast you sample the signal, you can afford to be slower, right? But if you have a very high pitch sound like that, can you afford to be so lazy now? You cannot, right? So when the signal is of high frequency, you better sample more often, right? So how fast you need to sample actually depends on what's the frequency content of your signal, right? Depends on the frequency content of the signal, right? So again, if you want to be kiasu, no matter what signal that comes in, I sample the highest that I can sample, right? But you're going to waste a lot of storage space, right? And computation later also. No point, right? You want to kiasu, everything will work. Like just now we add a lot of zero, it work, right? But if you so the question is how fast is enough? Okay, how fast is enough? Now in information theory, in this kind of sampling theory, there is something called Nyquist rate. Nyquist rate. They'll tell you, if you tell me what's the highest frequency in the signal that you are trying to sample, the minimum sampling frequency is so much. Okay? This is what we need to know. And you need to know this because you're going to use this for your project, understand? So if you want to analyze some signals or whatever, you must know what kind of frequency you need to use, right? Of course, you can be kiasu. You can do kiasu. You do some. You use the highest that people use, right? And you still work, of course, right? So. To understand the sampling theory, right? There are a few things that you need to understand. I'll use MATLAB to illustrate the concept. Okay. Once you understand the concept, things will become quite easy actually. Sampling is not a terribly difficult topic to understand. Okay. So you all scan already, right? The attendance, right? Now, I'm going to do something here, something. Some results that will be useful to understand sampling. Okay? Okay? Now, if you have an A signal, I don't use signal A again. We use signal in S. Signal equal to 0, 0. I don't use 0. I use 3, 2, 4, for example. Okay, my signal is 3, 2, 4. Okay. Now I have an impulse function. Right, impulse. I call it IM. Right, that happens at 0, 0, 0, 1, 0, 0, right? Right? Now, to convolve these two signals, right, you should use your hand to go and calculate, but I'm just using MATLAB to illustrate the result, right? Right? Now, if you want to convolve the two signals, right? The convolution of this signal, C and C6, is equal to, say, linear convolution. We talk about linear convolution first. Signal with IM, right? Right? And then let's see what happens. Right? You have your signal, right? You have your impulse function, and then what was my C6? C6. Right? So you see what happened now? Can you tell me what happened? When you have a signal and you convolve with an you convolve with something with an impulse inside, what is the result? What's the result? The signal gets shifted to where the impulse is, right? Right? Okay? Now you can change any number. You can use hand to compute. This is actually very important result, and it's actually extremely simple to derive. Say if I change to any number, I can have negative 5, negative 4, 8, or whatever, or 9 or whatever. It's still the same, understand? It's still the same, understand? Can you see that? Let me plot 6 IM. Understand? Yeah? So when you convolve with the impulse. That's the best thing in the world, you know. You don't need to do anything, you just move your signal to where the impulse is, understand? Okay? So convolution with an impulse is extremely simple. Just copy the signal and where the impulse is. Okay? Now what happens if you have a train of impulses? Let's say IM2 is equal to is 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, for example. Okay? Right? And then you see what happened. In MATLAB, we comment it with semicolon, means it doesn't speed up. It's not verbal. Okay? So you have signal IM2, and then C2 is equal to convolve signal, convolve signal with IM2, and then you see what happens. So this is what happened now. Your signal is still the same, right? Minus 249. Your impulse is an impulse train now. That's a train of impulses, right? 1, 1, 1, right? At different intervals. You see the result? The result is, okay, if I see an impulse here, I copy the signal here. Minus 249, right? Right? Signal is minus 249, right? And then if I see another impulse here, I just copy it here. If I see an impulse here, I copy it here, understand? Okay? Okay? So in other words, when you see an impulse or a train of impulses and you ask to do the convolution, you should be very happy because you don't have to do anything, just copy the signal there, right? Yeah? And this is done using convolution, right? Now, what is the significance? What is the significance of this? Why do I care? I hope your computer is still working. Why do I care about train of impulses? The train of impulses I care a lot because it actually mimics the action of doing sampling, understand? Okay? That means if I have some audio signal, right? And if I want to sample them, I can use an array, right? Or in fact, if I use a train, not an array. I mean, because we're in a continuous axis, right? Continuous axis with impulses, right? And I just I just call it with impulses, right? And you multiply this array at that time you want to sample them, right? And then you get the results, understand? Do you understand what I'm saying? Are you sure no question? There should be question now. Yes?
For sampling, are you talking about element-wise multiplying with the...
Yes, element-wise multiply.
Not convolution.
Element-wise multiply, yes. There should be a question. I'm talking on continuous axis, right? Continuous axis, in continuous axis, what's the magnitude of the impulse? Infinity, right? But what's the width of the impulse? Close to 0. What's the multiplication of infinity and close to 0? Just take it equal to 1, okay? We are not in the maths department here, we can get away with this. Just 1, equal to 1. So you have an impulse with your continuous time, you sample this, and then you put it one point, right? And then 0, another impulse, right? So the very action of doing the sampling can be described mathematically using impulse function, understand? Pick the impulse at where you want to sample that, understand? Okay? And why convolution? I'll explain later, but you have to understand that it's the sampling process. It's like if I want to sample the sound, right? I open my ear for a very short period of time and close it, understand? open and close, open and close, open and close. Understand? That's it. That's sampling, right? That's sampling, right? Okay. Okay, very good. Now. So remember this, if you have time domain signal and you want to sample them, it's mathematically equivalent to having impulses in the continuous time frequency domain and multiply with the signal, right? Right? And then you take the values, right? That's sampling, right? Okay? Now, when you have a time domain signal, your music, and your time domain impulses, impulse train, right? Train of impulses, right? When you multiply the two signals in the frequency domain, it is what? Remember, Fourier transform has got this duality principle. For Fourier transform, inverse Fourier transform. What happens in one direction, the other direction also happens. Because Fourier transform and inverse Fourier transform is essentially the same, right? Just the equation is just the same, right? Just a negative sign in the e to the power j, right? Yeah? So, in other words, when you multiply a signal, the two signals in time domain, in the frequency domain, it becomes a convolution of that two signals, understand? Okay? Just now what we learned was, when you multiply two signals in the time domain, in frequency domain, it is when you convolve two signals, what we learned earlier on was, when you convolve two signals in the time domain, in the frequency domain is multiplication, right? Now the other way around is also true. When you multiply two time signals in the time domain, in the frequency domain, it becomes convolution, no? So you convolve two signals in the frequency domain, in the time domain is multiplication, alright? Alright? It's the two, it works both ways. Okay? So now, in the act of doing sampling is the multiplication in the time domain, right? Right? So the act of sampling in the frequency domain is the convolution of the two signals, yes? Yes or no? Yeah? The convolution of two signals. So in other words, the music, right, has got a representation in the frequency domain, right? And the other signal is the train of impulses, right? You want to find out what's the frequency representation of the train of impulses. Okay? Now the very fortunate thing here is we are very lucky. A train of impulses in the time domain, the frequency domain is also a train of impulses, understand? That's a very unique Fourier transform property. In fact, there are two types of signals. I think 2 or 3 types, I can't remember, but it's 2 types of signals that you do Fourier transform, the shape is still the same, understand? Train of impulses is one of them. You get a train of impulses there also. The other one is a Gaussian signal. You do the Fourier transform of a Gaussian, the other side is also a Gaussian, understand? So let me show you why. I mean, we're not. I'm not telling you why, but I'm just verifying for you. Okay. So now you have, let's say, let me off this. So you have IM2, right? Right. Now, if my IM2 is FFT of IM2, right? Right. And then I want to plot it. Okay. I want to plot it. No, I don't plot it, but I just display it. Okay, let me show it's complex numbers with phase, but let me show you the magnitude. I show you the magnitude. Sorry, the train of impulses has to be of same interval. of same interval, then it will work. Oh, I should time 3 here, sorry. See, IM3 is a train of impulses, right? Yeah? And then the Fourier transform, the magnitude of the Fourier transform, right? Magnitude of Fourier transform is also a train of impulses, correct? Correct? Okay? Here got three zeros in between, here 2 zeros in between only, right? Okay? So we are very lucky. The train of impulses in the time domain, when you do Fourier transform, is also a train of impulses, understand? Okay? So in other words, if you have some signal, do re mi fa so whatever, some signal, like you sing a song, whatever. In the frequency domain, you have some signal, right? In the frequency domain, the frequency axis. When you sample your song in the time domain, which is the train of impulses, right? Use it to sample your song, right? In the frequency domain is also a train of impulses, right? But now you do instead of multiplying in the time domain, now it's a convolution here, right? So it's a convolution in the act of sampling in the time domain is the convolution of your original song with a train of impulses, right? Yeah? And isn't it very nice because we know that something convolved with the train of impulses is just sitting copy on where the impulse is, right? We just did it, correct? Yes or no? You understand perfectly? Do you? Yes? Who don't understand? This is a very critical thing. I say again, if you have a piece of music, some song, and you sample them, right? And the act of sampling is to multiply it with a train of impulses, right? And multiplying the train of impulse, multiplying the time domain is equivalent to convolution in the frequency domain, right? So you take the song, frequency domain of the song. You take the impulse, train of impulses in the time domain. The Fourier transform happens to be another train of impulses here. And we know that the convolution of the signal with the train of impulses here in the frequency domain is nothing more than just copy the signal and where the impulses is, right? Yes? So this is critical, okay? Now I ask you another question. Let's say, you see now you have 3 0 in time domain, your sampling is 3 0, right? The train of impulses, 3 zeros in between, right? And now you have 2 zeros in between, right? In the frequency domain. Now, let's say if I add another 0 here, add the 0. You add a 0 here means the sampling is faster or slower. This is a sampling in the time domain. Sampling time domain. Add 0 and then impulse. Add 0 impulse. Is faster or slower? Slower, right? If it is slower, then you look at the frequency domain. If you look at the frequency domain, what happened? Just now, your train of wait. Now it's like that. does that add as 0? Let me see. Because this is one period and okay, let me do this, huh? Let me do this. In fact I sample it more often, right? I sample it more often. Then you see I sample it more often. What do you see here? If I sample it more often, right? The output here has got more zeros in between now, right? Right? Which means that if I sample faster, right? Just now that was a wrong demo because I changed the length. Change the length has got different meaning already. I keep the same length, right? I keep the same length. Now instead of sample wait for 30, sample wait for 30, right? Now I sample 0, sample 101010, right? I sample more often, right? Right? When I sample more often, in the frequency domain, the impulse strings is further apart or narrower. It's further apart, right? Or more zeros in between now, right? Yeah? Yeah? Or more zeros in between now. And that's good news. You know why? Because in the frequency domain, you are going to convolve the signal with the trained impulses, right? If the trained impulses are very far apart, you can have full copy here, and a copy here, right? Yeah, many copies here, right? Right? So you keep your signal, understand? Now what happens if you sample very slowly? You sample very slowly, that means here in the time domain, here wait for a while, here wait for a while, right? In frequency domain, it will be the other way around, right? In frequency domain, all the impulses will be close together, understand? Okay? And when the impulses are close together, you're in trouble because if you have a signal here, you copy it here, right? You have another signal here, you copy here, the two clash, understand? And when the two clash, you are done. You're finished. It's something called aliasing. You always hear the word aliasing. You do computer graphics, also aliasing, right? Aliasing. Aliasing means this, understand? You destroy your music. Okay? You don't want them to clash. Okay? You don't want them to clash. Once you clash, you destroy your music. Because if they are far apart, the signals are all intact, right? All you need to do is, okay, I want to keep this part of the spectrum, and then I can recover the entire music, understand? Do you understand? Okay? So that's what sampling is all about. Today I give you an overview, it's 11:40 now. I need to release you now. Next week we continue with the slides, and the slides is just going to repeat whatever I told you just now, understand? Okay? Now, remember, I'm going to give you the tutorial today. The tutorial today, please spend good effort to do it. I think it's a fun tutorial, and you need to do it because you're going to use it for your project. The project will be individual project. Okay?